Hi Stats students, this is the first Chapter 9 video. Hopefully you've watched both Chapter 8 videos and you've been working on your Wiley assignments. This is the last chapter in our class, just Chapter 9, and we're done. So I'm going to split this one up again into two videos. We're going to do sort of the lesson and the first situation in this first video, and then we'll finish the lesson in the second video. But let me first tell you what you're going to need to complete this video. So I'm not sure what your situations are at home. I don't know if you have access to a printer, but if you do, then you'll go under content and you'll find our test 4 material. This is obviously your Chapter 9 packet. It's a little different than our other packets because it's only 1 page of lesson. And then after that, it's 18 examples. And that is because hypothesis tests, really, there's only so much you can say, and then you really just need to do it. You need to get in and you need to do the examples. So I have pulled all 18 of these examples right off of Wiley. This is your Wiley homework and your Wiley quiz. So make sure you have this ready and you'll be able to zoom through both of those assignments. Now, the other thing that you're going to need, if you can print it, is this little sheet. This is called the Chapter 9 reference sheet. So this is labeled a reference sheet. And this is sort of what I call my cheat sheet. This has all the quick and dirty information that I'm going to turn to as I'm teaching you this so that everything is in one place. So we have some handwritten material here. We have our 3 situations here. First situation being if sigma is known. That's what we're going to learn today. Second situation being if sigma is unknown. And third situation if we have a proportion. And those should sound familiar to you because those are the same 3 situations that we encountered in Chapter 8. So we're just using those again, but this time we're doing them with hypothesis testing. And then I have all kinds of steps for you to follow. So if you don't have a printer, my suggestion is to pull up this reference sheet and take a screenshot of each page. And that way, when you do go on to Wiley, you can pull up that screenshot and you still have this handy, okay? All right, so let's jump right in. Let's talk about hypothesis testing. So hypothesis testing is done in science, of course, because it's got the word hypothesis in it. It's also done by almost every major corporation in the world, especially if they produce a product. Because what they want to make sure of is that the product they're producing lives up to the quality and the standards that they are promising. So they test their products. The quality control department does a lot of this hypothesis testing. On the other side of that coin, a lot of consumer protection agencies do hypothesis testing because we don't want to just trust the companies. We want to make sure that what they're saying is true. So these consumer protection agencies also go in and do this testing and make sure that the companies are giving you the correct information. Okay, so let's just go ahead. Let's learn the language. Hypothesis testing has a lot of language that's foreign to you. So let's talk about some terms. 2 very important terms. You have the null hypothesis, which is HO, and you have the alternative hypothesis, which is H1. Now the null, we usually just call it the null. This is a claim or a statement about a population parameter. So we're talking about either mu or p, okay, that is assumed to be true until it's declared false. So we are going to assume that this product is exactly what the company says it is, unless we're able to prove otherwise. It's also kind of like that saying, you're innocent until proven guilty. Even if there's some suspicion that the item is not quite what it should be, we still have to assume it is until we can prove otherwise. And so that's what the null says. Okay, the alternative hypothesis would be whatever the null is not. So these are opposites of each other. So the alternative hypothesis is a claim about the same population parameter that will be declared true if the null is declared false. So if it's not this one, if this one is declared false, guess who's true? The alternative. Okay? So you have two choices here. We're going to make a null hypothesis. We're going to make a claim here. Then we're going to have to test it. The test is going to be the opposite of whatever we claim the null is. That's the alternative. Okay? Once we make that test, you have two choices. You can reject the null. In that case, your alternative is true. Or you can fail to reject the null. This is sort of like you accept it. We're not allowed to use the A word. We cannot say that we accept the null. We can never say that the null is true. Why? Well, it's just not quite how it's done in science and statistics. Instead, you have to make one of these two choices. So if you reject it, the alternative is true. If you fail to reject it, we just keep it the way it is. So we can't say we accept it, we just have to fail to reject it, okay? So this would be if the null is true. All right, here we go. So rejecting the null means the null hypothesis is false and we declare the alternative to be true. Okay, now let's get into some terms that we're going to have to use when we perform these tests. You are going to have a region, and by the way, we are going to be using these normal distribution curves. You're going to have one or two regions underneath the curve where we reject the null, okay? That region, and we'll get into where that would be because it varies by the specific problem, but the rejection region would be a region under our curve where we would have to reject the null, okay? So of course there would also be a non-rejection region, so we'll get into that. Okay, we also have what we call critical points. These are one or two values that divide your rejection region from your non-rejection region. So we're going to have to be able to find these critical points because they're the ones that create the regions. All right. Then we have two types of errors that can occur. We have a type 1 error, which is very important, and a type 2 error. Our type 1 error, sometimes called an alpha error, that's not an A, that's that little alpha, that's just the best my computer can do. This is an error that occurs when a true null hypothesis is rejected. So this is the worst kind of error. It's kind of like if you had an innocent person and they went to jail. They were found guilty. It's the worst error you can make, right? You have a true null hypothesis, but you reject it anyway. Well, we're all human, so we all make mistakes. This is an error that occurs sometimes. Now, it's called an alpha error. Alpha is the same thing as the significance level. Okay, same thing. These occur interchangeably. It's also called the probability of making a type 1 error. So 3 different ways of saying the same thing. I know this is confusing. I hate that we're having to do this through a YouTube video, but you're going to get the hang of it. So significance level, alpha, the probability of making a type 1 error, these are all the same thing. So alpha could be described as the probability that the null, that's H of O, is rejected given HO is true. Okay. All right, well, what about the second type of error? The type 2 error is called a beta error. That's not just a B, that's actually beta. This is an error that occurs when a false null hypothesis is not rejected. Now remember, we can't accept it. We can only reject or fail to reject. So if we have a false null and we don't reject it, that is a type 2 error. That's kind of like when you have someone guilty, but they go free. Okay, it's not great, but at least you didn't have an innocent person going to jail. So it's not quite as bad as the type 1, but it's still an error, still an issue. And so if we were to make a probability out of that, that's the probability that the null is not rejected given the null is false. Okay, so beta is the probability of making a type 2 error. He doesn't have a fancy level like alpha does. But we do call the power of the test 1 minus beta. You don't see that a lot. And that's the probability of not making a type 2 error. Okay. All right, so we have 3 possibilities for a test, not to be confused with our 3 situations, which are sigma's known, sigma's unknown, population. Okay, we actually have 3 possibilities for a test. We have a two-tailed test. Okay, in this case, we have a rejection region in both tails. That's why it's called a two-tailed test, because in both tails you have a rejection region. Let's draw a little picture. Let's say this is our curve. Okay, pretend it's really fabulous here. You have a critical value here and a critical value here, and you have 2 rejection regions. Those are both rejection regions. And then in the middle, you have a non-rejection region. So this is a rejection region, this is a rejection region. And these rejection regions, that's alpha. That's what makes up your rejection regions. So since I have 2, I have to divide alpha by 2. And there we go. Okay, rejection regions in both tails. Here's your non-rejection region. They're separated by these little z values. Yep, we're back to the z values. And those are critical values. Okay. All right, so what would my null and what would my alternative hypothesis be for a two-tailed test? Well, your null would be that your population parameter equals a number. Your alternative would be that it does not equal a number. Anytime you see an alternative hypothesis that's not equal to, that means you have a two-tailed test. That's your giveaway, okay? All right, let's talk about a left-tailed test. Okay, you can probably guess where that rejection region is. We only have 1, and the rejection region is in the left tail. Okay, so if I draw my curve, I had to draw it a little flatter there so I don't get up into the other guy. Okay, I only have 1 left tail. There's my rejection region. I'm only going to have 1 critical value, right? Because I only have this 1 separation. This whole big thing is going to be the non-rejection region. And this is going to be alpha. I don't have to divide it by 2 or anything. There we go. Okay, so what would your null look like? Well, let's talk instead about what your alternative would look like. Your alternative is the one that decides what kind of test you have. So how would I make a symbol for a left-tailed test? Less than. Oops, oh my goodness, I wrote it in the wrong thing. Sorry, kiddos. Let me fix that. There we go. Okay, so less than indicates left-tailed, and the alternative is the one that chooses which test you have. So the null is going to be the opposite of this. So it might be equal, or it might be greater than or equal to, okay? Usually what you're gonna find is that all of the nulls are equals. So they don't really give you any information. The alternative is what's gonna give you the information. So a right-tailed test is going to have your rejection region in the right tail. So here we go. Here we go. We make a rejection region over here in the right. Now where you put that border and how big that region is, that's really up to you. All you need to do is make sure you know that you have a shaded in rejection region of alpha somewhere in the right tail. And everything else is a non-rejection region. Now, how are we going to indicate the right tail is the rejection region? Greater than. This is what's going to tell us we have a right-tailed test. Okay, so your null may be an equal sign. They usually are always equal signs. Or he could be the opposite of what you see here, which would be less than or less than and equal to. Okay, so again, here's the important takeaway of that. Always look at the alternative hypothesis to determine the type of test. That's what determines it, not the null, okay? Make sure you make a note of that. All right, so that kind of gives you an overview of how to deal with hypothesis testing. Now I know we have one more little piece down here, so let's go ahead and do that, and then we're going to flip the page over and do one more little general review. Okay, well guess what's never going away? The CLT. There's your central limit theorem. So this is just down here to remind you, because it may pop up on Wiley, that we can only use these formulas and this great big main idea if n times p is greater than 5 and n times q is greater than 5, okay? So if they ask, can we use the CLT? Can we pretend it's normally distributed? Well, perform these two little formulas and go from there. Okay, let's turn it over. This is a little chart that I copied off of Wiley. Okay, I'm gonna try to just leave it just like that so we can use it. Okay, it's not super duper great, but it helps answer a few questions here and there. All right, here we go. So, possible hypothesis test outcomes. So, the actual situation and the decision, okay? Let's find out, what we're trying to find out is, did we make the correct decision? Or did we create a type 1 error? Or did we create a type 2 error? So, 3 possibilities: correct decision, type 1 error, type 2 error. This would be an alpha error, this would be a beta error. Okay, here we go. What if our null was true and we do not reject it? We have a true null and we do not reject it. Well, that's perfect. That is actually the correct decision. Remember, we can't accept anything. So this is the closest we get to actually accepting. Okay? So if it's true and you do not reject it, awesome. That's the correct decision. Okay? What if the null is false and we do not reject it? Uh-oh. It was false and we do not reject it. Okay, that's not the correct decision because it was false. This is a type 2 or a beta error. Okay, this is what we talked about when somebody is guilty, but they do not go to jail, they go free. Okay, that would be that type 2 error. All right, let's try this line. We have a true null hypothesis, but we reject it. We rejected it, but it was true. That's the big bad one. That is the type 1 error or the alpha error. Okay, that's the one that really we messed up on. That's the situation where someone is innocent, but we found them guilty and we put them in jail. Okay. All right, let's try this one. The null is false and we reject it. Let's think about that. It's a false null and we reject it. Well, that sounds like the correct decision. We did the right thing there. Okay, so just a different way of thinking about this. They're going to ask you some of these scenarios and you want to be able to really think those through. Okay, let's do this little chart one more time. Okay, if this is what we're dealing with, this is what we have. Rejection region is shaded. Oh, we got one here. We got one here. I have 2 rejection regions. What kind of test is this? This is a two-tailed test. That's what that is. All right. So this little part in here that's not shaded, that's our non-rejection region. Awesome. This is going to be critical values. Critical value 1, critical value 2. All right. Okay, so what little symbols am I going to put in here? For the null, it doesn't really matter. You can put equals for every null. What am I going to put in here for the alternative? This is the important one. For a two-tailed test, the alternative gets not equal to, right? Not equal to. Okay, next one. Here we go. I have a shaded rejection region over here in the right tail. So what kind of test do I have? A right-tailed test. This would be my non-rejection region. I would have one little critical value because I just have one border there. Okay, if I go up here to my null and my alternative, doesn't really matter what you put in for the null. You can put equals, you can put whatever you want. Here's what matters. What are you going to put in for the alternative for a right-tailed test? Greater than, right? So you could have put in for the null, you could put in a less than, you could put a less than or equal to. You got a lot of options for the null, but this is the important one that has to match the type of test you have. Okay, and then last but not least, rejection region over here in the left means we have left-tailed test. Here's our non-rejection region. Here's our one critical value. Notice these little stars here. They represent critical values. That's what those are, okay? All right, so again, doesn't matter what you put in for the null. What matters is the alternative. And for the left-tailed test, your alternative better be less than. Okay, so for your null, you could have equals, you could have greater than, you could have greater than and equal to, whatever. I always just put equals because that way I don't have to think about it. Okay, all right, good job. Okay, here we go. We're actually going to start some problems now. Okay, here we are. We're starting on problem number 1, and we are going to go through problem number 6. Is where we're headed on this, okay? Through problem number 6. Okay, so let's go and look at our little reference sheet real quick. Let's just see what's on there before we jump right in. So everything you see on the front is exactly what we just did. You get your 3 types of tests. You get to see all kinds of information about them, including how to write the alternative hypothesis. You talk about alpha a little bit, and you're told to look at H1 to determine the type of test. So that's a nice little concise piece of information. Okay, then let's go to this first page. Here's our first situation. This is going to be problems 1 through 6. And that's why we're going to do those first. If sigma is known, everybody remember what sigma is? Sigma is your population standard deviation. If sigma is known, this is what we're going to follow. Here's your 2 formulas you're going to need. Now, notice there are 2 approaches to doing a hypothesis test. You can do the entire test using just what we call a p-value approach, or you can do the entire test using what we call a critical value approach. So in our textbook at IRSC and through our stats department, we want you to learn both, because honestly, there is value to both of these approaches. And if you were to continue on and you were to go into statistics, you would need to know both of these approaches. So we're going to make sure that you know how to do both of them. This critical value approach is what we have sort of already been working on a little bit, because it actually has critical values, right? And so, and we call alpha the area. So all those pictures we've been drawing, that has really just been focused on the critical value approach. The critical value approach, and I'm just going to draw a left-tailed test here. Critical value approach worries about regions. This is a region approach, okay? So you would have a rejection region, you would have a non-rejection region, and you would have a critical value, a Z critical, that would separate these regions. Then your rejection region is also known as alpha, or the significance level. You're going to calculate what we call a Z observed value and see where on the number line Z observed falls. If it's smaller than Z critical, you reject the null. If it's larger than Z critical, you don't. You fail to reject. And so that's how the critical value approach works. Okay, it's a very visual approach. The p-value approach, unfortunately, is almost opposite. So it gets very confusing. That's why I have written these little things out in steps. The p-value approach is very different. So we're still using our curves. Okay, we're still using our curves. Let's say we did a left-tailed test with this. You don't have critical values on the p-value approach. No critical values. That's only for the critical value approach. So this little device here, this one that divides these 2 regions here, is going to be Z observed, okay, in the p-value approach. This area, rather than being a rejection region, is the probability, because that's what P stands for, the probability that a specific event is going to occur, okay, and that would be the null. This is the probability that the null is true, okay? And so what's happening here is that this area is your p-value, the probability that your null is true, okay? And then what you're going to do is use alpha as your significance value, okay, and see, is your alpha larger than the probability or smaller than the probability? How significant is it? Is it significant enough to make you reject? Well, it is if it's larger than your p-value, larger than your probability. Or is it not significant enough? That would be if it's smaller than your probability. Okay, so it's a very different approach. We are going to do both of these numerous times, so you're going to get the hang of it. But I just wanted to let you know what we have done so far is strictly critical value, and now we're going to have to stop and also consider that there's another way to approach this. Okay. All right, so here we go. Number 1. Okay, number 1 says we have a random sample of 120 observations. Okay, so we have a sample of this. We know that's N. And this produced a sample mean that is X bar of 29. Now here's the key to hypothesis testing. You have to know your symbols. If you can't pull out this information from this sentence, you're in trouble. You want to make sure you can do that. Find the critical and observed values for Z. Okay, when I see this, I know I'm going to use a critical value approach. So it told me which approach I needed to use. It will always tell you what approach to use, or it will tell you to choose. So once you have practiced each approach enough, you're going to develop one you like better. And so when you do get those rare problems that say, just tell us what to do, reject or fail to reject, you get to pick the approach that you want to use. Okay, but for now, for this particular problem, we want the critical approach. Okay, using alpha, here's an alpha of 0.01. Okay, the population standard deviation is known. Oh, good. That's sigma. Sigma is known. That's the type of problem we're dealing with. And it's known to be 9. Awesome. So this would be the page we're on. We're down here. We know sigma's known, and we are going to follow these 3 steps, and we're going to be able to complete our problem. So that's kind of how you use this reference packet, okay? So I went to sigma's known, I went to critical value approach, I'm going to go boom, 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 and then I have my problem, okay? Here we go. We are given a null, that 0 got a little big, okay? Doesn't give us any information, just equals to 28, versus the alternative. That gives us some info. What kind of test is this when we have not equal to? That is a two-tail test. All right, folks, so here we go. Two-tailed test means we have a rejection area in each tail. Here's the non-rejection area in the middle region, non-rejection region. Now, since we have both of these here like this, for the Z critical, for the critical value approach, alpha is your rejection region, but I have 2. So I'm going to have to take alpha divided by 2 since I have 2 regions. Okay, well, my alpha is 0.01, so 0.01 divided by 2, this is going to give me 0.005. Can you see that? Is that okay? We'll scoot him over just a little. There you go. Okay, 0.005. That's what we're looking at in each one of those. And we're going to have a critical value here and a critical value here. Now remember, this is 0 right here. So this critical value is going to be negative, and this critical value is going to be positive. Okay, they're going to be the same number, but this one's negative and this one's positive. All right, well, here we go. I'm going to get my steps. I've written all over my paper, but here are my steps. Okay, I'm going to fold this so I have it down here like this. Okay. All right, critical value approach. Number 1, calculate Z observed from the above formula. All right, well, I already folded my paper. Here we go. Okay, so I want to find Z observed. I have X bar, it's 29. I have mu. Now, a lot of students are going to go, where's mu? I don't have mu. Look where mu is. Mu is your null every single time. Mu is your null, okay? I do need sigma X bar, and here's my formula for that. So here we go. Sigma X bar is sigma over square root of n. 9 over square root of 120. Okay, I'm going to go out quite a few decimal places here. Now I'm going to find Z observed. Now I do want to go ahead and tell you that Z observed is sometimes called the test statistic. I think Wiley uses both. So in Wiley, make a note, if it asks you for the test statistic, that is Z observed. Okay, that's from that formula. Okay, here we go. We're going to take X bar minus mu, that comes right from the null, over 0.82158. That's going to give us Z observed. And I came up with 1.22. Okay. Awesome. Okay. Number 2, find Z critical. Okay, I actually have 2 Z criticals. I have a right one and a left one. Using alpha as the area in inverse norm. If you have a two-tailed test, divide alpha by 2 first. Well, we already did that, thank goodness. Okay, so we are going to go to inverse norm in our calculator. We're going to put in this alpha divided by 2 area, comma 0, comma 1. Okay, here we go. All right, I'm going to go second bars. That was my distribution. I'm going to go down here to inverse norm. There it is. It wants the area 0.005. That's alpha, but I had to divide it by 2 because I have a two-tailed test. 0, 1. Okay. You get to put 1 in. Don't put 9 in because we are assuming that we are standard normal. There's my Z critical. Notice it's negative, so that means it's going to be our left Z critical, and I'm going to round it. What do we think our right Z critical is going to be? Same thing, only positive. Okay, so that came right from my calculator. All right, so Z critical right is 2.58. Z critical left is negative 2.58. We're actually done with this problem. That's all it wants. But just for practice, if we were to determine whether we reject or fail to reject, what I'm going to do is I've created this chart now. I've got my critical values. I'm going to take my Z observed. What region does 1.22 fall in? Well, 1.22 would be like about right here, right? That's definitely non-rejection region. I just figure out on my number line where this would fall. And in this case, he's non-rejection. So I would fail to reject the null. Remember, I have 2 choices. I reject or I fail to reject. And because it was in the non-rejection region, I failed to reject. That is how you would work your critical value approach on a sigma is known problem, okay, with a two-tailed test. All right, let's go on to number 2. All right, here we go. We have a 2 and a 3 on this page. Okay, number 2, a random sample of 16 observations, all right, N is 16. Taken from a population, produced a sample mean, there's your X bar, of 75.4. The population is normally distributed with a standard deviation of 6. What kind of standard deviation is this? Population, tells you right here in the sentence. So sigma is known and it's going to be 6. Great, because we get to use this sheet again. Okay, I hate that I wrote all over it, but there it is. Okay, let's see what else we're dealing with. Here's our null. It doesn't tell me a whole lot, except it does give me mu. I'm going to need that. Here's what's going to tell me what I need to know. What kind of test are we doing? Mu is greater than 72. Greater than means we're going to be doing a right tail test. Right tail test. Okay, we can do this. All right, now read ahead to tell you what approach. Look what now, we want a p-value. So we're going to be sigma is known, p-value approach. So this is new. We haven't done this before. Now, oh, I just realized I have a number 1, a number 2, and another number 2. Okay. So now we're going to use these 3 steps. So clear your mind. We're no longer looking at regions. We're no longer thinking about critical values. Take a deep breath, wipe that away. Okay. I'm going to fold this. I don't even want to look at it. Okay. No critical values, completely different p-value approach. Okay. Well, I know I have a right-tailed test, so I'm going to draw this with a right tail. I'm not going to label this a critical value now. I am going to shade this in, but this is going to be my p-value. This is the probability that mu is 72. That's what this is. What we want to know is once we get done testing, once we find some values, is what we found significant enough to change this? That's what we do with a p-value test. Remember, p is probability. Okay, p-value approach. We're just going to follow these little, we're going to follow our steps and then we'll fill in what we have when we have it. First step, calculate z observed from the above formula. So notice these 2 formulas that you see at the top, they're for both approaches. You have to have these completed whether you use the p-value or the critical value approach. They're for both. Okay, and remember, z observed is sometimes called the test statistic. It's the same thing. All right, so let's calculate. First thing we're going to need is sigma x bar. Okay, we're going to have sigma divided by the square root of 16. I get 1.5. Okay, now we're going to use our formula for z observed. Remember, that's our test statistic. Okay, that's this guy right here. I need x bar, 75.4, minus mu. Don't panic, mu's not over here. Mu's your null. Divided by sigma x bar. Okay, there just weren't any other decimal places, or I would have gone out further, but it's just, that's what it came out to be. Okay, so 2.27, that is my z observed. That is actually going to go right here. That's what that value is. Notice it's positive. That's a good thing. It should be positive. That's what we would expect, right? Because this is 0. So that's good. Okay, now we're still trying to find our p-value, by the way. Here's what it says to do. Use z observed, okay? Find the area under the curve, because that's what the p-value is. We're trying to find this area under the curve. We're going to use normal CDF. We have a right-tailed test. So here's our lower bound. Our upper bound is infinity, 0 and 1. This reminds you what to do if it's a left-tailed test. And for a two-tailed test, you can use either one, okay? All right, so here we go. We're going to our calculator. So remember, for the critical value approach, we used inverse norm. For the p-value approach, we're using normal CDF. Okay, so a little different there, normal CDF. Here we go. All right, so we said according to what we have, our lower bound is 2.27. Our upper bound is infinity. We do a 0 and a 1. There's our p-value. Our p-value is going to be 0.0116. I'm going to take it out 4 decimal places. So A wanted the p-value. That's our p-value. Okay. So p-value, it came from normal CDF, right? We did a lower bound. We did an upper bound, a 0 and a 1, and we came up with 0.0116. That is the probability that our mu is correct. Okay? All right. So we completed A. This is A. All right, B. If the significance level, that's alpha, is 0.01, would you reject the null? Well, I don't know. I have to see how significant would that be compared to our result. Okay, well, let's see. If I look at, I'm trying to find a place to put this where you can still see it. Okay, I'm going to compare the p-value. If alpha is greater than the p-value, okay, it's more significant than what we have, we reject. If alpha is less than the p-value, it's not significant enough to make us change our mind. We fail to reject. Okay, so here's alpha. When I compare it with my p-value, okay, when I compare it with my p-value, I see that alpha is actually less than the p-value. 0.01 is smaller than 0.0116. So I am going to fail to reject the null. Remember, I can't accept it, but I'm not going to change anything. I'm not going to do anything. I'm going to leave it alone. If this bothers you, fill in zeros and compare it then so that everybody has 4 decimal places. And then you'll see that this is indeed smaller. That means that 0.01 could fit in here. Our probability is so much bigger than this that we are not interested in changing our null. We're going to leave it alone. Okay? It's not significant enough to make us change our mind. All right, C. Okay. What is this significant? What if, whoops, that's supposed to be an if, the significance level is 0.025? Okay. What if we have a larger significance level? Well, in that case, that's greater than the p-value. 0.025 is greater than 0.0116, right? It's greater than this probability. That is significant enough for us to say, oh, hold up, we are going to reject the null. Okay, we're going to change some things. It's larger than our rejection area. So you can tell that this significance level is extremely important. In this particular statistics class, we don't get into finding how you would find the significance level. We don't do that. We just take what's given and test it. But in a higher level class, they will get into exactly how you find this and how you determine what is significant and what isn't. But you can tell it makes a big difference, right? How significant you want that particular item to be, especially with a p-value test. So that's how you handle it. You find your p-value, which is just your area, normal CDF, and then you compare that alpha, that significance level, and you decide, is it significant enough to change it? Well, not if it's smaller than this. Or is it larger than your p-value? In that case, yes, it is significant enough and you need to reject. Okay. All right, let's look at number 3. Okay, we hop around a lot. So now we're hopping back to look. Critical. Okay, we're going back to critical. So take a breath. Okay, get p-value out of your mind. We're going back to regions. We're going back to critical values. Okay, we're going to go from there. All right. This says a random sample of 118 observations produced a sample mean of 33. Again, make sure you know what these symbols stand for. Find the critical and observed values of Z, so this is a critical value approach, for the following test of hypothesis using alpha as 0.05. The population standard deviation is known, okay, and it's 9. All right, So we know we are back on this page, but we're down here on critical value approach now. All right, let's see what kind of test we have. Here's our null. Doesn't tell us anything except for mu. Here's the alternative. Here's what we know. Just so happens we're back to a right tail test. Okay. All right. So here we go. Here's our right tail. Critical value means we're back to regions. This is a non-rejection region, and we're going to have a critical value right here. Also means this is alpha. Just so happens we have it. And we don't have to divide it by 2 because we don't have to split it like we did the two-tailed, right? There we go. All right. Well, let's fill in these values. So if I go to my paper, first thing it wants me to do, calculate Z observed. Remember, that's your test statistic from the above formula. Okey-doke. Here's my formulas. So I'm going to have sigma x bar, that's going to be 9, divided by square root of 118. I got 0.8285. Now I'm going to find Z observed. That's going to be x bar minus mu. Remember, mu's over here. He's HO. He's your null. Divided by 0.8285. And that gives me 6.04. Holy cow, that's a big Z. Okay, there's our Z observed. I'm going to put this in right here, 6.04. Okay, now so far, all of our Z observed have been positive. We do get negative Z observed sometimes though. That happens, especially with left-tailed tests. So it just so happens that's what we've gotten so far. Okay, step number 2, find Z critical using alpha as the area in inverse norm. All right, so I'm going back to inverse norm. Remember, that's your calculator. I'm putting alpha in as my area, comma 0, comma 1. Okay, here we go. Normal CDF is for the p-value approach. Inverse norm is the critical value. So I went second vars because I wanted that distribution menu down to inverse norm. Put in my alpha. I get negative 1.64. Now, do we think we should write negative 1.64 here? No, this is a right tail test. We're going to write positive 1.64. Why did it give me a negative? Well, remember, this area that you're putting in here is supposed to be the area to the left, and we put in the area to the right. That's why it's messing us up a little bit, but it's not a big deal. We just have to remember this should be a positive critical value. Now, if we wanted to be really, really correct, I know that the whole area under here is 1. I could do 1 minus 0.05, and that would give me that this portion is 0.95. So if I did that, 0.95, then I get the positive version. So you can do it with the added step in there and really think about the fact that we're looking for the area to the left when we do inverse norm, or you can just throw in alpha, remembering to make it positive if you have a right-tailed test, okay? All right, so that's my critical value. All right, that's all it asked for, so that problem is actually done. But if we were to decide to continue this, this is my critical value, this is my observed value on my number line. Where does 6.04 fall? Oh gosh, it's like way on down here, right? I mean, way on down here. 6.04 is like way down here. That's definitely rejection region. So even though it doesn't ask for it, we know we're actually going to reject the null if that decision needed to be made, okay? All right, 2 more, 3 more, sorry about that, 3 more. Okay, here we go. This is what would be considered a complete hypothesis test, okay? This would be the whole thing. So here we go. We're going to start at the top. So the manufacturer of auto batteries claims that the mean life of the batteries is 45 months. So maybe that's what's on the packaging. Maybe that's what they're advertising on TV. Our batteries last 45 months. Well, a consumer protection agency wants to check this claim. So they took a random sample of 24 batteries. All right. They found that the mean life for this sample is 43.40 months. That's going to be X bar. That's the mean of the sample. Okay. Using a normal distribution with a population standard deviation of 4.5, oh good, sigma's known, and it's 4.5. Find the null, the alternative, and the p-value. Okay, so sigma's known, we want p-value approach, and we're going to have to write everything, okay? When the alternate hypothesis states that the mean life of these batteries is less than 45 months. Once we've done all that, we want to know, do we reject the null at a significance level of 2.5%? Okay, this is a real deal problem here. All right, we are going to need to write the null and the alternative. Okay, since we're dealing with sigma known, we're dealing with mu. Our null, we can always write equals. What is the null? What is the claim that we are investigating? Right here. The claim is that the batteries, the mean life is 45 months. So that's what we're looking at. That's the null. Okay. The alternate hypothesis, or the alternative, says the mean life is less than 45 months. What does this tell us? What kind of test are we looking at? A left-tailed test. So there, we wrote the null, we wrote the alternative, and we determined we're looking at a left-tailed test. All from just this paragraph. That's pretty good, guys. Okay, now what we're going to do is find the p-value. Okay, so we're going to go to our little page here, sigma's known. We are going to look at the probability value approach, the p-value, and we're just going to go right down the line. Okay, so here we go. We're not interested in regions anymore. We are not interested in critical values. We're interested in p-values. That's this area here. This is going to be our z observed. All right, here's 0. What do we expect our z observed to be, positive or negative? I hope you said negative. Good. Okay, first step, calculate z observed from the above formula. You have to have that in order to get the p-value. So that's why we're doing that first, even though all we're looking for is the p-value. Okay, here we go. We're going to find sigma x bar. That's going to be sigma divided by the square root of n. That's going to give us 0.9186. Now we want z observed. Remember, that's also called the test statistic. We're going to have x bar 43.40 minus mu, that's 45, divided by sigma x bar. We're going to round that to 2 places. Sure enough, it's negative. Awesome, we thought it would be. There we go. Okay, now let's find the p-value. To find the p-value, we are going to use z observed and find the area under the curve using normal CDF. Okay, so going to our distributions, we have a left-tailed test. Our lower bound is going to be negative infinity. Our upper bound is this negative 1.74, and we're going to put in 0 and 1. That's going to give us the p-value. Okay, so we're going to go normal, CDF, lower bound, negative infinity, upper bound, negative 1.74, comma 0, comma 1. Here we go. We're not interested in inverse norm anymore. Let's clear that. We're going second vars. We're going down to normal CDF, negative infinity to negative 1.74, 0, 1. Okay, just like this. Enter. There's our p-value, 0.0409. Okay. That's the probability that mu is 45. Okay, here we go. That's all they wanted for this paragraph. The null, the alternative, the p-value. Now this next sentence says, will you reject the null at a significance level of 2.5%? Significance level is alpha. Now we don't want a percent, so how do we change that to a decimal? We're going to divide by 2, right? So we're actually looking at 0.025 as our alpha. That's our significance level. Now remember, we compare it to our p-value to see, is it significant enough to change our null? Okay, well let's look and see. Turns out alpha is smaller than our p-value because 0.025 is less than 0.0409. It's smaller than this probability area. So we're going to fail to reject. We're not going to change anything. What the battery company is claiming is true. This is fine. They are claiming the truth, okay? So we're going to fail to reject because alpha is smaller. It's not significant enough to make us change. So will you reject the null? No. I will not reject the null. I will fail to reject the null. Okay? And there you go. That was a complete, full, normal hypothesis test. That's a pretty big deal. You created everything. So good job on that one. And that was the p-value approach. Okay, let's try another one with that p-value approach. This one came right off a Wiley quiz. You can tell that because look, it has drop-down menus. I just copied and pasted. So this is one of those quiz questions. All right, we have the Lazarus Steel Corporation, and they produce iron rods that are supposed to be 36 inches long, okay? Well, you can already tell that's going to be mu, right? You guys are experts now. The machine that makes these rods does not produce each rod exactly 36 inches long. The lengths of the rods are normally distributed and they vary slightly. Well, that's understandable, okay? It is known that when the machine is working properly, the mean length of the rods is 36 inches. So that's the goal when it's working properly. The standard deviation of the lengths of all the rods produced on this machine is always equal to this. Guess what that is? That's sigma. Remember, sigma is your population standard deviation. And even though it doesn't say population standard deviation, it says all. That's population. So that's a tricky one, but sigma's known. And this is it, okay? The quality control department at the company takes a sample of 20 rods every week, and they calculate the mean length of these rods, and they test the null hypothesis. We knew that was going to be the null, against the alternative hypothesis, which is this. Notice it's just not equal to, because we don't really care if it's less than or greater than. The problem is if it's not 36. So this is the null. This is going to be a two-tailed test. Okay. If the null is rejected, the machine is stopped. They have to shut down production and they have to adjust the machine. A recent sample of 20 rods produced a mean length, okay, that's a sample mean, of 36.015 inches. Calculate the p-value for this test of hypothesis. Based on this p-value, will the quality control inspector decide to stop the machine and adjust it if he chooses the maximum probability of a type 1 error, this is alpha, to be 0.025? Okay, well, I don't have to tell you that there's going to be some very unhappy people if he stops that machine for no reason. So we have to decide, do we tell him to stop it and make adjustments? Or do we say, no, it's all right, it's doing pretty good? Okay, here we go. So this is the information that we have. We even know alpha. Okay. All right, we know our null. Null happens to be mu is 36. The alternative that I guess they just have to constantly test is it not 36? And this, ladies and gentlemen, is a two-tailed test. Now, we did a two-tailed test for critical value, but we haven't done one for p-value. And it's a little different because remember, your p-value is your area under the curve. And now with a two-tailed, we'll have two areas. So we need to just practice this and make sure that we understand what's happening here. Okay, so we're gonna have a p-value. Here's our two-tailed test. Okay, we have our two areas. Here's our p-value here and a p-value here. Okay, there we go. All right, so we're going to sigma's known. We're going to p-value approach. We're going to calculate z observed from the formula. So we're first going to do sigma x bar, and then we're going to do z observed. Okay, here we go. Sigma x bar is sigma, oops, I put my decimal point in the wrong place. Sigma divided by square root of n. Okay. I got that to be 0.007826. I went out really far on this because if I only went 4 decimal places, 2 of them are 0. So I tried to get at least 4 that aren't zeros. Okay, my z observed, or my test statistic, is going to be x bar minus mu divided by sigma x bar, and I get 1.92. Oh, I don't know why I wrote a 6. 1.92. Okay, so remember, with p-values approaches, this is the observed. And in this case, I have 2 of them. So I go down here. This one's going to go right here because it's positive. I'm going to need another one over here, and it's going to have to be negative. So I'm going to have to change it to negative 1.92 and put it there. Okay. Now I have 2 p-values. Okay, here we go. So second step is that I want to be able to find the p-value. So I'm going to use z observed, and I'm going to find the area under the curve using normal CDF. No big deal. Here's the issue. Okay. The issue is that normal CDF is only going to find one of these. So you could find this area using left-tailed test. You could find this area using the right-tailed test. It really doesn't matter. You can use either one. But since you have a two-tailed test, you have to multiply your answer by 2. Because we're looking at the total probability, this probability plus this probability, when we compare it to alpha to see the significance. Even though they're separated, we are looking for the total probability to see if the significance level is such that we need to shut this machine down. So it really doesn't matter which one of these you choose. I'm just going to choose left tail because it's there. So my lower bound is going to be negative infinity. My upper bound is negative 1.92, comma 0, comma 1. And by the way, you could find normal CDF for this and normal CDF for this and add them together. You'll get the same thing. Okay, here we go. I'm going to normal CDF. Whoops. Okay, I've got a lower bound. I'm going to put in an upper bound, and I get 0.0274. Okay, 0.0274. This is only one shaded region. We have two. We are going to have to multiply by 2 to get the total p-value, to get both, because this is 0.0274 and this is 0.0274, and our p-value is going to be both of these. So either add them together or multiply by 2. Either way, your p-value is 0.0548. That is our p-value. That's what we would write in this little blank on our Wiley quiz, okay? Because it says round our answer to 4 decimal places. All right, so we found the p-value. Based on the p-value, are we stopping the machine or not? Okay, well, if we reject the null, then we're stopping the machine. If we fail to reject the null, we're not stopping the machine. Okay, so here we go. We're going to compare our alpha. Alpha is 0.025. The total p-value, and that's what we're looking at, so the total p-value is 0.0548. Alpha is significantly less than our p-value. Significantly less. It's even smaller than one little region, much less both of them added together. So we are going to fail to reject the null. And if you're confused about that, you always can look right on here and it will immediately tell you whether to reject or not reject, okay? So we're going to fail to reject the null. So if we're failing to reject the null, the machine is fine. The machine is fine. We're failing to reject. Now, this is going to be a drop-down menu because this came right off Wiley quiz. So when you drop it down, it's going to give you choices. The choice you want is does not need adjustment. That's what you're looking for, okay? And that's going to be the one that's correct, okay? All right, so that was another real world giant sigma is known problem. Okay, one real quick one and we're going to stop for today. Okay, so very quickly, this is almost a trick question. I only put it on here because I get so many calls and emails about it. Number 6, for the following significance level, what's the probability of making a type 1 error? Alpha equals 0.06. Well, guess what, folks? Alpha is the significance level, and alpha is the probability of making a type 1 error. These are all the same thing. So if this is alpha, what's the probability of making a type 1 error? It's 0.06. It's the same thing. So that was a really tricky question. Okay, well, that leaves us to start number 7 with video number 2. We'll come back and do that. In the meantime, I hope you're doing well and not going too stir crazy. And keep up with your Wiley. I'll talk to you soon. Miss you. Bye-bye.